Okay, our next speaker is Dr. Dharmalingam Ganesan.
That's right.
Did I get that? From the University of Maryland.
Thank you. I'm going to talk about how we did model-based testing of a software bus. It's part of the core flight executive that you have been hearing many times during this week. It's a joint work with Mikael Lindvall, who's my supervisor at Fraunhofer, and Dave from NASA Goddard, who is also here, who can help us in CFE-related questions. All right. I'll take a quick look at traditional test automation. When people say, usually they say test automation, they really mean running the tests that are manually put together. So this automation is only for running the tests. It's like more like store and replay kind of tests, essentially. Test cases are manually constructed. The problem is that it's effort intensive and also unable to cover many of the off-nominal scenarios usually. There are quite a few could cover, but not many. Coverage issue, and then tests are also too detailed. It doesn't give us a high-level overview of what we are testing. And it's difficult to handle multitasking architectures like the CFE that I'm going to talk about.
Can you stay in front of the mic?
Oh, I'm sorry. Oh, I'm sorry. Not easy to test multitasking architecture. I'm going to talk more about this later. Okay, model-based testing. Tester develops a model, what we call testing models, instead of writing individual test cases. Usually, we write test case 1, 2, 3, and so on. Instead of doing that, we create a model. And then the model becomes the test oracle for comparing the implementation behavior. In this paradigm, test cases are automatically generated from the model based on requirements, API documentations, etc. What are the key benefits of model-based testing? Testers work at a higher level of abstraction, so not programming level details are abstracted, and innumerable number of test cases can be generated because it's a model. It's like a finite state machine in the end. We can trigger quite a lot of off-nominal scenarios. I don't claim we will be able to cover all the off-nominal scenarios, but quite a lot. And we get a precise specification of the behavior that the system should satisfy because of the modeling. All right. Let's take a quick look at the system under test. I don't have to speak a lot here. It seems many of us know about CFS these days. The core flight software system is a product line which provides reusable modules for NASA missions. It's developed at Goddard, implemented in C. And I'm going to talk mostly about the CFE layer, which is part of the CFS framework. The good news, it's also an open source framework, the CFE layer. And here's this context diagram. I would like to show the software bus. That's the focus of today's talk. You have software bus, and all these bubbles, essentially runtime tasks, communicate by publishing and subscribing to messages. So the software bus is like a broker, basically. And we wanted to apply model-based testing on the software bus because software bus is the core of the CFE layer, helps for communication. And already there are unit tests developed by the NASA Goddard team, of course. They have pretty good coverage, but the tests don't take into consideration the multitasking architecture that I just shown in the earlier slide. So the goal of our work is to apply model-based testing ideas to software bus and see whether we can apply it, first of all, generate test cases for the software bus, and essentially generate a lot of bubbles that you saw on the previous slide. We want to generate a lot of fake bubbles that will do publish, subscribe, and see whether the messages come to the subscriber properly. All right. We want to demonstrate the applicability of model-based testing. Okay. So we developed an approach for testing the software bus and allowing for multitasking architecture in particular. Okay. What is in our current model? I'll talk about the model syntax in a moment. We model very basic things like creating a pipe, which is the core thing you need to do when you're doing a pub-sub architecture-based system. You need to be able to have a pipe to receive messages, right? Like a queue, basically. And we can delete a pipe, we can subscribe to messages, send messages, receive messages, and we can instantiate multiple apps or the bubbles. These are the things we have currently modeled. And we are able to generate a lot of test cases from that model. And the tool that we used for this project is based on Microsoft Spec Explorer, which is a plugin to Visual Studio. I'll get back to this later. What are the challenges of testing a software bus? Well, to test a software bus, we need apps that can publish and subscribe, right? Otherwise, how do we know the software bus works correctly? Well, apps are also runtime tasks that communicate using the bus. But the problem here is each app cannot decide on its own the correctness, right? If I subscribe to a message and I'm receiving a message, well, it depends whether somebody else published a message or not. So the order of execution matters. So you can't have one test that decide on its own the system is doing correct or not. So that's a problem. Correctness depends on the global state of the system. And the order of execution of the tasks matters. That's why we need a test architecture to test these kinds of systems. So we thought about an architecture style, sort of a style to test publish, subscribe, multitasking systems. What we thought was a parent-child architecture paradigm. You could consider like a master-slave paradigm. What the idea here is we will treat each test case as a parent. The parent controls the child. It makes sense. And the children are sort of slaves. They will do the job the parent says and give the results back to the parent. And the parent decides whether the children behaves correctly or not. That's the idea of this test architecture. What we are doing here is that at runtime, we create a lot of tasks based on the model. And then each task does the job according to the expectation of the parent and send the results back. And the test assertions are part of the parent. Okay? These things should be clearer when I show you a concrete example. We don't really write a lot of child tasks code. We write only one task code, and then we instantiate the same code for multiple tasks. So a parent can have many children, but use the same code base. That's the idea. But there is still a challenge here. How do we communicate from parent to child? We are talking about multitasking architecture. If parent is a master task, children are all independent tasks. How do we communicate? So we thought about, why not let's use the same software bus itself to communicate between parent and child, get the results, and then check the correctness. So roughly, this is the bigger picture. I'll talk about it in more detail. What you see here is the CFE, which is the core flight executive software bus. And we have a parent, if I can show you here. This is the parent. It's basically one test case. It has a result pipe. It subscribes to results, okay? The children can have multiple pipes, although I just shown one pipe on the picture. They wait for commands. So they have a command pipe, and they say, I'm ready to do whatever you want, father or dad. And children are waiting for the commands from the dad. And parent just publishes commands. Okay, child 1, you do subscribe. Tell me what was the return code. The child will put the result into the result pipe through the software bus. And now the parent decide, is the return code correct? If I subscribe to a message once, and if I subscribe it again, the result should be false, right? Because I already subscribed according to the specification. So the parent has that logic to decide the correctness of the child. That's the idea. Okay. So pretty much what I said is encoded here. Each child task subscribe to all commands. In this case, create pipe, delete pipe, subscribe, unsubscribe, and things like that. Parent broadcasts the command to all child tasks. And the child with the proper task ID does the magic, basically talk to the CFE bus, get the result, put it back as a broadcast message, but only the parent subscribe to the result message, so the parent will get the result. Okay. Child performs the task, send the return code to the parent. Parent verifies the assertion. Okay. That's the bigger picture. Okay, let's get back to the tool that we used. Tester develops a model using the Spec Explorer tool. A model, in this case, is a model program. Okay. It runs as a plugin to the Visual Studio environment. We used 2010. Model programs are written in C#-like syntax. There are also modeling libraries as part of this package. A model program is basically a simplified version of the system under test. That's a problem. What does it mean by simplified version? I'm going to talk about it soon. Imagine there's a lightweight version of the program that you're testing. You have another program for it. Okay. Spec Explorer would analyze our model programs and generate state machines. Once you get the state machines, you have everything you need to generate test cases, right? So there's also a question of how do we validate the model itself is correct. So you could put invariance to the model and check whether your model is free of errors. Like at the model level, I would like to be able to check if I subscribe to a message and I unsubscribe, the return code should be false or true. So whatever the specification you have encoded, we can let the invariant checker to explore the model and see whether there are any places it violates the property. Anyway, that's just to get the confidence at the modeling time. Test cases are automatically derived from the state machines. And then the system under test is triggered for individual test cases and see whether there is any discrepancy between the model's expectation and the system under test expectation. So if a test fails, it doesn't mean there's a bug in the system under test. It could be a bug in the model itself, because model is yet another program, but just it's a guiding thing to derive test cases for us. Okay. So what are the abstractions for the model program? I talked about the simplified version. You can't have a simplified version, right? There is a reason why the original program is complex. A lot of functionality implemented, a lot of error handling code and whatnot, right? So how can I create another program which is very simplified than the original program? It's very difficult, right? That comes the abstraction. The idea is that don't create exactly the same copy of the implementation, of course. Create a lighter version of it. Nobody wants to create 2 times the same system. Nobody wants to do that. We don't have time to maintain 2 implementations and don't have time to develop those 2 systems, actually. So the idea is to apply very simplified abstractions. I'm going to talk about it. For example, in the real implementation of the software bus, it deals with complexity related to multitasking, right? It deals with message structures, very complicated. I mean, it's simplified, but still complicated, I would say. C structures, structures within structures. There's quite a lot of complexity in managing the message structure. And it uses concurrency paradigms like semaphores, mutex, and so on. So the real implementation is sophisticated, of course. But we don't need all of those sophistication for our test program. Like, we want to write a lightweight version of the software bus using very simplified constructs. That's what we mean by the abstractions. Okay. So, for example, we don't need to model the recursive C structure. We could just say a message is just an integer. I subscribe to 1. If you publish 1, I should get it. 1 itself is not a meaningful message, right? I'm just saying, in the real implementation, you have a lot of structures and hierarchies within the message, but we make a simplified assumption. And in the real implementation, you would have message queues or pipes. In the model, you could have a simple structure. You could just have a sequence or a list. You can even abstract away the complete queue and just count how many messages on the queue. So you could make abstractions in a way you like it. Finite depth for the queue. And we don't use pointers, threads, semaphores at the model level. Make it extremely simple. Very simple, basic data types, integer, booleans, and maps. Okay. There's also cost of doing this abstraction, of course. We will not be able to cover all the behaviors the system under test has. The idea here is that by carefully choosing the abstraction, we may be able to cover quite a lot of details. That's the idea. Okay. So how does a model program look like? Model program itself is a C# code. So we can view it like this. We have a bunch of configuration parameters. For example, how many apps do you want to have in your model? How many pipes do you want to have? And what is the depth of the pipe? And so on. These are model level configuration parameters. Then you want to have the ability to represent the state of the bus. How many connections to the bus? What are the messages in each pipe? All these things you have to keep track. And then in the model exploration, you may get states like infinite state space. Whenever you add a new element to a queue or a pipe, you're changing the state of the system, right? So essentially, software bus is an infinite state space. You can't test it theoretically. So you make assumption, well, if the state space, if the size of the pipe is more than 5, I exclude it from my tests. So you define so-called state filters that exclude states that you don't like to cover in your tests. And when is it good to stop a test? What are the accepting state conditions for each test case? For example, you want every test case to end up in clean state, like clearing up all the resources and so on. So you could define accepting state conditions in the model. Where is the actual meat of the logic, basically, is so-called rule methods. So if you look at the CFS API or the CFE software bus API, there's publish, subscribe, unsubscribe, and so on. we have a copy of that in a lighter version of the copy implemented in so-called rule methods that does the real logic. The rule methods update the state of the system based on the guards. So the guards are something unique here. They're called preconditions. So when can I do subscribe? Well, only if you have not subscribed earlier, right, to the same message. Only if you have already app that was created, and so on, the other conditions. And then, since the rule methods are also real functions, you need arguments and values. So you could generate those values using so-called domain generators. I'll show you examples, and then there are some helpers as well. Okay. So I talked about the state data. How does it look like? Well, very simple. For example, well, you have a hash map that keeps track of what are the subscriptions to individual pipes. So subscription is kept track by this particular map. What are the messages in each pipe? So you have another hash map to keep track of that. And then how many elements are in each pipe? Okay. The overall system state is based on this map, which for every task you have this data. Every task means every bubble on the bubble diagram has this data. So the overall system state is basically captured here in the task data map. So the rule methods basically update this task data map. And whenever you update, you get a new state. So the idea is to capture the system state in a very simplified notation like basic sets, integers, sequences, and abstract away from the complexity due to threading and concurrency and so on to make it simple. Okay. So how does a model program really look like? So you write individual functions like a regular program essentially. However, there is a small difference. You see something called condition.isTrue. That's a precondition. Only if the precondition is true, a particular rule can be enabled. There's a notion of enableness. So you don't really call these rules in other places. Like in traditional programming, you would call functions from other functions. Here, it's automatically called based on some kind of a rule-based paradigm, meaning if the precondition is satisfied, it will fire up. Okay? And that's basically the set of rules. Okay. What are the guards? Okay, I talked about the guards. If you go back quickly to the previous slide, for example, can I create a pipe? Well, only if you are allowed to create a pipe, you are allowed to change the state of the system. Okay? What does it do? Well, it checks whether you already created a pipe, because you're not allowed to create a pipe again and again. It checks whether the task name is valid. All these basic properties are checked here. The mouse. These are the basic properties we want the system state to hold true, so that can create pipe will go ahead and say, yes, you can go ahead and create a pipe. Okay? All right. Once you put together a model, the state space is infinite, as I said. Any integer paradigm, any integer argument, you can plug it in 0, 1, 2, 3, 4, 5, infinite number of test cases, right? So you create so-called slices to restrict the state space. So in this case, for example, I'm interested only in testing whether subscribe and unsubscribe work correctly. Okay? So I define a very specialized slice. I say, I create a task like a regular expression, bunch of tasks, bunch of pipes. I do subscribe, unsubscribe in interleaving. This is interleaving, okay? I don't care which order subscribe and unsubscribe are called. And then I end up with deleting the pipe, deleting the task, and I repeat. So I define a specific constraint of how my state space should look like in the end. And the Spec Explorer tool will analyze my slice and produce a state model like that automatically from my C# code. In traditional model-based environment, people usually draw these states manually, and then they generate test cases. In this case, the model program is encoded first, and then a tool traverses the program and builds the state space. So you may wonder, what are these states, essentially? Well, these states are the values for the state data that I showed earlier. It has bunch of apps, bunch of pipes. What are the values? It's just like a memory map of what is inside this data structure. So whenever you change the data structure, the rule methods usually change the data structure value. You get a new state. Okay, that's the idea. All right, once the state machine is there, you're now almost done with testing, right? Because if you walk through the state machine, you could generate test cases, right? One test case is initialize a task, create a pipe, unsubscribe, subscribe, delete a pipe, delete a task. you could take different paths in the graph and generate a lot of test cases. Okay, the arguments I have not explained. Very briefly, create a pipe in this case means app0 is creating a pipe with the name 0 of depth 1. So just logical representation of the different arguments. Okay. These are the test cases that would come up automatically once you have the state machine model.
Wait, so what is the terminating condition in this state diagram?
Okay, so you see, I'm sorry, I didn't explain that. There's a S14 which has a green color, which is the accepting state. So I define so-called accepting state in the model. So when is it good to stop? As I said, only after you delete a task you are allowed to terminate. So you encode that. That's right. Otherwise, the test case may look very sometimes stupid, like init a task and then it's done. It doesn't do anything useful. So you define accepting states. Okay, so individual test cases just for testing a simple scenario of subscribe, unsubscribe would end up with this many test cases. I don't think a human would come up with this many because it's explored automatically through the different arguments. Okay. All right. So what is the way we need to execute the test cases? The system under test speaks a different language, right? It's based on C language. It has a different type of data types. So we need to bridge the gap between the model-generated test case and the system under test case. So we need to create so-called adapter that essentially converts the data types into the appropriate data type. For example, in the model, I say create a pipe, and I say pipe name is 0. Okay? The 0 may not be sensible at the API level. The API requires a string as a pipe name, so we have to map 0 to a particular string. So we do all these translation at the adapter level to make it work at the real API level. Okay. So we invented our own sort of abstracted interfaces for testing, sort of. These wrappers essentially will convert all of the things that you saw on the model into specific concrete syntax. Okay. And our generated test case would look like this. One test case says, parent initialize first as an application to CFS. And we check whether application initialization is successful. You see there's an assert. Then we say create a pipe. We want to check whether pipe assertion is successful, right? We have created an app with a pipe name 0 of depth 1. All these things are coming from the model. So it's not put together manually. So we can run this test case, and we can find any discrepancy. So what are the advantages of using model-based testing? Well, the model focuses on the domain, right? I talked about the concept of publish, subscribe without going into the details of the actual syntax. Not much. And instead of working at the source code level, we work at the higher level of abstraction. We could generate a lot of test cases. And the information is in one place. If I want to understand my test cases, I go back to the model and see individual slices. Okay? And test cases, of course, can be run over and over again. So what are the advantages of using this particular tool from Microsoft is generated tests are pretty readable. I walked through it. And one interesting thing I found is that the infinite space can be sliced into finite number of scenarios using the regular expression-like language. That's pretty neat. So you could have small models to reason about, to visualize, and so on. And models are programs. So if you're a programmer who likes programming, this is a good way to go. And models can also be verified rigorously. Okay. We are also having some challenges. It's not all that great. There are some challenges. Modeling errors can lead to infinite state space. Just having an integer argument to one of the rule methods will go into out-of-memory error because Spec Explorer will try each and every integer in the world, of course, an infinite number of integers. And for example, if you have a queue and you didn't carefully design that queue depth, every time you insert a new element, the system is changing the state. So those kind of things can be tricky. You will get used to it once you start into the details, of course. Completeness of the slice, another problem. You take a model and you slice it into smaller pieces. How do you know that your slices are complete? Meaning, if you take a union of the slices, how do you know that you covered everything? Model debugging is sometimes tricky. Sometimes I see a new state. I don't understand why do I get a new state. So you have to do a fair amount of debugging to understand that. And invariance can be violated and without giving any concrete example. That's another problem. I talked mostly about the software bus. What about the other flight software? Well, you could apply this technology, which we have done in quite a few cases, to other systems. The only a few requirements, I must say, the software must have an interface. You should be able to trigger the API or the GUI or whatever, and you should be able to send commands and receive reply. And you need some specification, otherwise it doesn't work. I mean, how do you know that the test works correctly? Well, you need a specification. In contrast to the yesterday's talk from JPL, the Gerard Holzman talk, his talk is mostly about test coverage, but not related to test oracle. So his goal is to cover different paths and branches and lines, which is a great goal, of course. But we are talking about here more of functional correctness. You know? That's why we need specification. Well, optionally, we felt that if you have a bunch of test cases, like in the CFE case, we have a lot of test cases, so we could leverage that for our model building effort. That's another thing you may need. The conclusion of the talk is that we felt MBD works well for testing of multitasking architectures. In this case, the software bus. We have this parent-child test architecture paradigm to invoke multiple children and collect the results and decide at the parent level. That's a pretty interesting idea, at least from our point of view. Models and generated test cases become a very good specification. I can precisely explain how subscribe, unsubscribe works by just going back to the state machine and say, if you already subscribe, you can't subscribe again. All those things are encoded carefully in a state machine model. And a lot of test cases come out, of course, and they are not tightly coupled to the CFE software bus syntax. They are at a higher level of abstraction. If you start modeling new, you may have to be careful about the kind of details you put in the model. Again, if you model everything, your model will be as complex as the system that you're testing. So you have to make a careful decision of what factors you can leave out, how much you can abstract. You know, that's one thing that's non-trivial. It's kind of an art. All right, I'd like to acknowledge a few people here. Front of our intern, Jan, helped in executing the test cases, and the good thing is CF is open source, so it's open for the world. And Alan helped us in a few OSL-related questions, and this work is part of the SARP project funded by OSMA, and I would like to thank Martha, Ken, and Ricky for their contribution. And with that, I'm done, actually. Oh, thank you.
Can I ask a question?
Yes, sure.
Wait.
So anything model-based is pretty much, I think, kind of enables you to optimize. Isn't that true?
Yes, that's right.
So if it's a model-based testing, does it really help you to cover all the stressful cases and corner cases? Is that your goal, or is it kind of facilitates the testing, and what is the kind of your end goal? I mean,
that's an interesting question. Model-based testing definitely has the potential to cover off-nominal behaviors. There is an open question of how many test cases can you generate. I mean, you could generate theoretically infinite. Sure. If it's a loop, you could keep on walking. Right. So the next phase of the project, we want to take feedback from the system under test to decide how to guide the model exploration process. Exactly. I can keep on doing subscribe, unsubscribe, subscribe, unsubscribe. When do I stop? So there's a very interesting challenge there.
So at the end of the day, you want to be able to say, hey, this has been fully tested, right?
That's right. That's right. We want to be able to say that. Currently, we can measure code coverage and see how much we were able to cover from the model level. But there's also a trade-off here. Model is simplified version of the system under test, right? The system under test is really complex. It checks for everything. Like if you pass a pointer, it checks whether the pointer is null or not. Model doesn't do all those things. So we may not be able to trigger a test case that pass a null pointer to the API, right? So there are cases where we will not be able to cover through the model. What is interesting, though, here is more the functional-oriented errors that we can detect through this type of technique. And in particular, with the architecture style of publish-subscribe, there's a problem here. How do you test publishers and subscriber in isolation? I mean, they can't decide their performance on their own. I mean, the behavioral performance. So you need some kind of a sort of a parent or a guard to keep track of what's going on.
And how would you detect, or kind of like a racing condition?
Yes. So it's a very interesting question. We are able to handle multiple tasks.
Right.
But but the parent is controlling which task is currently running. So the granularity of multitasking is very limited in our case. So the next level of granularity will be to let a task run and stop in the middle of something, right? In our case, it's more like atomic. We don't interrupt, publish in the middle.
That's right.
That's a deeper question. Definitely very interesting to look into the future. Yeah.
Thank you.
Sure.
Could you please go back to the picture of the state machine?
Sure.
Yeah. So could you help me, where in this is the non-determinism? If you have multiple tasks that
Sure.
can create pipes and subscribe and unsubscribe in any order,
Sure.
that should be captured in a state machine, which I believe should be non-deterministic.
Sure.
Is this non-deterministic?
So this particular model looks at the multi-threading at a higher level of abstraction. Okay, it doesn't go into the details of let the publisher run one instruction and stop before completing all the instruction. So there is another model I can show you offline. I have it. We talk about non-determinism in a different form, meaning you subscribe to a message, but you don't know which message you would exactly get. In another system, the order in which the message comes is different from the order in which it was published. So in that case, at the modeling time, you can't really predict what will be the next message you will receive. So we have built-in non-determinism in that model. I can show you that model later, offline. Yeah.
Thank you.
Sure.
Any other questions? Very good.
Okay, what you're doing reminds me a little bit of RSpec and Cucumber, which are tools that are in the Ruby test-driven development culture. Pretty common. There's a lot of them, but those are two pretty common ones. And they do allow a certain amount of by using a DSL exactly as you did, you can describe these models very succinctly. So
That's
that
right.
someone who's not the programmer can understand that that's a reasonable representation of what we want out of the system. So I think that's really fantastic. I think that when you start getting into dealing with the multi-threading issues, because those are really challenging.
That's right.
Then I would suggest that you look at Gerard's spin, which does allow you to also describe a model. It's a different DSL than we're using, but it's the same. It's about the same amount of power, let me say, or abstraction. But it does allow you to sit there and say, well, sometimes it'll be this, and sometimes it'll be that.
Yes.
And it does do the interruption at a at the granularity that is actually happening inside the processor. So when it's a multi-core, multi-threaded processor, when you're hitting a cache, when you're stalled by cache and things like that, these things are modeled inside of the engine of Spin. Spin started out a long time ago, but Gerard keeps upgrading it so that it can deal with these low-level issues that crop up, and I do think that it's a challenging part of the problem, and rather than trying to reinvent it all yourself, I just suggest that
thank you for the suggestion. I'm actually aware of the Spin. I'm user of the Spin. In this work, the objective is to be able to generate tests where multiple apps can use the software bus. The unit tests that are developed manually by the engineers at NASA Goddard consider one app at a time. So there's only one app that's using the software bus. So the kind of bugs we may detect in this case are related to the data coming from multiple apps, because the basic test has only one app test, right? And you have multiple apps, but they're not really concurrently running because the parent is deciding which child to run and say, child, you stop now. I'm going to let the other child publish. So he's controlling the interleaving. Yeah, you're right. Thank you.
Any other questions? Nope. Thank you.
Thank you.